Welcome everyone. I am A.G. Parandhaman, working as an assistant professor in the Department of ECE at NPR College of Engineering and Technology, NATHAM. Today we are going to discuss about the fundamentals of satellite communication. First of all, what is a satellite? Satellite is nothing but an external body which revolves around the Earth. What is the purpose of satellite? Satellites are mostly used for the purpose of communication. The type of communication may be analog and digital, and mostly we are using satellites for long range communications. Now going into the topics which are going to be discussed now. First, the overview of the unit 1 is satellite orbits, which includes introduction, Kepler's laws, Newton's law, orbital parameters, orbital perturbations, station keeping, geostationary and non-geostationary orbits, look angle determination, limits of visibility, eclipse, subsatellite point, sun transit outage, launching procedures, and launch vehicles and propulsion. These are all the basic parameters which we are going to discuss with the unit 1. And now let's see each topic one by one. Before going into the satellites, let us know about the various frequency band designations. We are all well aware that frequency is nothing but the parameter which is used for the mainly for the purpose of communication. Mostly the frequency range starts from kilohertz, and it goes on up to terahertz and petahertz, etc. For satellite communication, we prefer mostly gigahertz communication, and the various bands are designated in the right hand side, which starts from VHF, UHF, L, S, C, X, KU, K, KA, V, W, MM, and MUM. The VHF is abbreviated as very high frequency, which is used for mobile and navigation purposes, and it is used mostly in weather satellites. The next band is UHF, which is ultra high frequency, which is used for television reception and other data related transmissions. The next is the L band, which is used for mobile satellite services and navigation systems. Navigation systems denote all the maritime navigation and air navigation. Next is C band, which is the common band, is used for fixed satellite services, and it is restricted to the frequency of 6 to 4 gigahertz. The next is the KU band, which is used mostly in the DBS satellite. DBS is nothing but direct broadcast satellite, and it is used in the frequency range of 14 to 12 gigahertz. Next is the frequency allocations. Who decides the frequency allocation? The frequency allocation is allotted by International Telecommunication Union. It is the union formed by the group of various countries across the globe. The ITU, in short, that is the abbreviation of International Telecommunication Union, splits the globe into 3 major regions. One is the region 1, which comprises of Europe, Africa, and Soviet Union and Mongolia, formerly Soviet Union and Mongolia. The region 2 comprises of North America, South America, and Greenland. The third one is the region 3, which is mostly covering Asia, Australia, and Southwest Pacific. These are the 3 regions which the satellite communication is broadly used in. Next is the types of orbits. There are 3 main categories of orbits. One is the low Earth orbit, next one is the medium Earth orbit, and the third one is the high Earth orbit. In low Earth orbit, the altitude range is around 375 to 1000 miles, and the frequency used here is up to the limit of 30 gigahertz. The satellites which are deployed in LEO, that is low Earth orbit range, has a revolution time of around 90 minutes, and the maximum time is up to 3 hours. The main advantages are the delay is very much reduced in this low Earth orbiting satellite, and the size of the satellites are very much small, and it is very much economical when compared to other satellites. It eliminates the need for bulky receiving equipments, that is the transceivers which are used in the onboard satellites, and it can be used for handling broadband data, which is used in most of the households. The next, the various subcategories of LEO are little, big, and mega LEOs. The main applications are vehicle tracking, environmental monitoring, and two-way data communication, which is used for short and narrowband communication. The main drawback of this LEO satellites is the small coverage area and its short lifespan. The lifespan is around 5 to 8 years. Next is our medium Earth orbiting satellites. So the altitudes range between 5,600 to 9,500 miles, and they are mostly used for the North Pole and South Pole communications. Next is the geosynchronous Earth orbit. The name synchronous stands for similar. So these satellites are in similar to the rotation of the Earth. So they are known as geosynchronous Earth orbit. So the orbit is in synchronous with the Earth's rotation. From the ground, when we see this satellite, they appears to be fixed with our plane level, and they are positioned at a height of 36,000 kilometers. And each satellite covers around 40% of our Earth when it is placed in geosynchronous Earth orbits. Next is the Kepler's law. So for a satellite to be placed in space and to deal with the satellite motion, Johannes Kepler have described 3 planetary laws which governs the motion of the satellite. So they are classified as Kepler's first law, Kepler's second law, and Kepler's third law. The main aim of this Kepler's law is to describe the planetary motion. So first of all, a satellite orbiting the Earth follow the same laws that rule the motion of the planets around the sun. That is, whatever the planets which revolve around the sun in the solar system, the same laws are applicable to a satellite rotating or revolving around the Earth. So Kepler's law apply quite generally to any two bodies in space which interact through gravitation. So the main principle of Kepler's law is gravitation. So it applies only for the bodies which are interacted through gravitation. Coming to the Kepler's first law, it states that the path followed by a satellite around the primary will be an ellipse. So obviously we know that there are two bodies. The one with higher mass will be considered an primary, and the another one which revolves or rotates around the primary will be considered the secondary. So he states that whichever body, that is the secondary, which revolves around the primary, the path followed by the secondary will always be an ellipse. Here consider an example where there is a path of an ellipse which has two focal points f1 and f2, and there are various parameters which deals with this ellipse. We have semi-major axis, semi-minor axis, and center of ellipse. So he stated the formula for the eccentricity E, which is given as E equals the square root of a square minus b square divided by a. Here the center of the mass of the two body system termed the barycenter is always at the center of the foci. Based on the value of eccentricity, we can decide which type of orbit the satellite is in. Example, if the value of eccentricity is equal to 0, then the orbit is a circular. When the eccentricity value lies between 0 and 1, it is an elliptical orbit. So if the value of E is very much high, then the shape of the ellipse will be very much long and thin. Next, second is our Kepler's second law. The statement of Kepler's second law is that for equal time intervals, a satellite will sweep out equal areas in its orbital plane focused at the barycenter. So this is nothing but when a satellite is very much close to the Earth, it covers some area. Let us say the area covered by the satellite is A1 in the time period S1. If the satellite is very much farther to the Earth, let us consider the area covered is A2 and the time taken is S2. So according to Kepler's second law, the both areas A1 and A2 covered in the given interval of time is same. That is, it is equal, A1 equal to A2, given that S1 equal to S2. This is the major portions or major grasp we are getting from Kepler's second law. Next is the Kepler's third law. So it states that the square of the periodic time is proportional to the cube of the mean distance between the two bodies. It is given by the formula a cube equals mu divided by n square, where a is the major axis and mu is the Earth's geocentric gravitational constant, which is given as 3.986005 into 10 power 14 meter cube per second square, and n is the mean motion, which is given in radians per second. This is used to find the orbital period of the satellite. Next, apart from this, we will be discussing about Newton's law, because Newton's law is much needed for the launching of satellites. We know that satellites are launched using Newton's third law, that is, for every action there is an equal and opposite reaction. So before going through that, we should discuss about the Newton's first law and second law. Newton's first law is nothing but the law of inertia. It states that an object at rest will remain at rest unless acted upon by a unbalanced force. So that is nothing but an object tends to be in its state unless it is stopped or it is hindered by some other external forces. Next is the Newton's second law, which gives the expression for force, which is nothing but a force is the product of mass and acceleration. Mass denotes the weight of the object and acceleration is the speed of the object with respect to time. So when the mass is high, the force exerted on that object is also very much higher. Next is the Newton's third law, which is very much useful in the satellite communication for the launching of satellites. Here we all very well aware of that statement, that for every action there is an equal and opposite reaction, and that is to say that whenever an object pushes another object, it gets pushed back in equal force in the opposite direction. This is used for the launching of satellite. Next is the orbital parameters. There are around 14 orbital parameters which describe the position of the satellite in space. They are listed as subsatellite path, apogee, perigee, line of apsides, ascending node, descending node, and line of nodes, inclination, prograde orbit, retrograde orbit, argument of perigee, right ascension of ascending node, mean anomaly, and true anomaly. Let us discuss each one with specific examples. The first one is the subsatellite path, and it is nothing but the path traced out on the Earth's surface directly below the satellite. That is the path which the satellite follows. That is simply known as subsatellite path. Next is the apogee. Apogee is nothing but the point farthest from the Earth. So the point which is very at a very long distance from the Earth is known as apogee. Perigee is nothing but the point closest to the Earth. Line of apsides denote the line joining the perigee and apogee through the center of the Earth. When we join perigee and apogee by the center of the Earth, the imaginary line is termed as line of apsides. Next is the ascending node. The ascending node is nothing but the point where the orbit crosses the equatorial plane going from south to north. When we move from south to north, the imaginary line drawn is known as ascending node. Descending node is the inverse of the ascending node, that is the point where the orbit crosses the equatorial plane going from north to south. So this is an example of the orbit around the Earth, and the various parameters are listed below. So first is the apogee, the point which is very much longer distance from the Earth. Next is the perigee, which is the closest point to the Earth. Then line of apsides, the line joining both perigee and apogee through the center of the Earth is line of apsides. Next, inclination. Inclination is nothing but the angle between the equatorial plane and orbital plane. It is used for launching purpose. It is purely used for the purpose of launching the satellite or launching the vehicles which carries the satellites. Then here comes the line of nodes, ascending node, descending node, and various nodes which are associated with the satellite. The ascending node is, as we have discussed earlier, it goes from south to north. Next is the descending node, where it is the inverse of ascending node, that is the point where the orbit crosses the equator from north to south. And line of nodes is the line joining the both. Then line of nodes is nothing but the line joining the ascending and descending node through the center of their inclination. Inclination is the angle between orbital plane and Earth's equatorial plane. So then is the prograde orbit, the orbit in which satellite moves in the same direction as Earth's rotation. The angle for prograde orbit lies between 0 and 90 degree, whereas retrograde orbit is nothing but the satellite moves in a direction opposite to the Earth's rotation. That is, here the angle of inclination is 90 degree and 180 degree. So this is the explanation or pictorial representation of prograde orbit and retrograde orbit. And commercially, most satellites are launched in the prograde orbit because this orbit follows the same velocity as that of Earth. So there will be very much saving in fuel because we go with the gravitational force of Earth, whereas in retrograde we will be opposing the gravitational field. So there will be wastage of fuel and energy. So we prefer mostly prograde orbit. Next is the argument of perigee. This is the angle from ascending node to perigee. Next is right ascension of ascending node. This is the angle measured eastward in the equatorial plane from line of Aries to ascending node. Line of Aries is nothing but an imaginary line which goes through the center of the sun. Then mean anomaly. Mean anomaly gives the average value of the position of the satellite, whereas true anomaly gives the absolute value of the position of the satellite. So the argument of perigee, mean anomaly and true anomaly are given here. Next is the orbital elements. We have discussed the 14 parameters which defines the satellite in the space. Among them, the major 6 elements are confined to be called as Keplerian element sets. The major elements are semi-major axis, eccentricity, mean anomaly, argument of perigee, inclination, and right ascension of ascending node. These 6 elements are referred to as Keplerian element set. Next is orbital perturbation. Perturbation is nothing but the external disturbances which affects the motion of the satellite in space. The disturbances may be because of the gravitational force of sun, the moon, and other meteorite impacts, or for the disturbances by some other scrap satellites. So these are the main conditions which affect the motion of the satellite. Whatever it is discussed is theoretically an orbit described by Kepler is ideal when it is considered to be a perfect uniform spherical mass. So thank you for listening to this lecture. Once again, thank you everyone.